Hello class, welcome to the Stat 215 Lecture 15 video. In this video, we're going to learn about the properties of and applications for the following continuous distributions: the exponential, the gamma, the chi-squared, the beta, and the log normal. Let's start by looking at the exponential distribution. For the exponential distribution, let x be a continuous random variable with probability density function f of x equals 1 over beta e to the negative x over beta, where x is greater than 0 and we'll allow it to be 0 otherwise. X has an exponential distribution with parameter beta. This idea of the parameter beta is similar to in the normal distribution when we had U as their mean and sigma as our standard deviation. Different distributions are dependent on particular parameters. So when we are working with our exponential distribution, the expected value of x is going to be equivalent to beta, and the variance of x will be equivalent to beta square. At this point, let's talk about how our exponential distribution is related to our Poisson process. So if we recall, we use the Poisson distribution to find the probability a certain number of outcomes occurs in a specified period of time. And we can recall that our PDF for the Poisson distribution was e to the negative lambda t multiplied by lambda t to the x over x factorial, where x was equal to 0, 1, 2, and so far. We may also recall that lambda is the average number of outcomes per unit of time, and t was the multiplier of the unit of time. But sometimes our time period is a random variable. So for example, if we let our random variable t be let our random variable t be the time between arrivals at a congested intersection, then our arrival is a Poisson event. However, if we let an example be that we let our random variable t be the time it takes for one person to be served at a hot dog stand, this is a completed transaction in a Poisson event. So by using our Poisson distribution, the probability that no events occur in the span up to t amount of time would be, using our PDF, e to the negative lambda t multiplied by lambda t to the 0 over 0 factorial. This would simplify to be e to the negative lambda t. So if we suppose that a random variable x is the time to the first Poisson event, then the probability of x greater than x is the same as the probability that no Poisson events will occur in up to x amount of time, meaning that the probability of x greater than x would be equivalent to e to the negative lambda x. Now, how this connects to our exponential distribution. So we've allowed that the probability of x greater than x is equal to e to the negative lambda x. This means that our CDF f of x would be equivalent to the probability of 0 less than or equal to x less than or equal to x, which would equal 1 minus e to the negative lambda x. Then we would find our f of x to be equivalent to 0 minus e to the negative lambda x multiplied by negative lambda, which would be equivalent to lambda e to the negative lambda x. So therefore, x has an exponential distribution with beta equal to 1 over lambda. Now we can recall that lambda is the average number of outcomes per unit of time, so therefore beta is actually the average time between events. Let's take a look at an example of this. So suppose a system contains a certain type of component whose time in years to failure is given by x, and that x follows an exponential distribution with mean time to failure at beta equals 5. What is the probability a given component is still functioning after 8 years? So by plugging into our PDF for the exponential function, we have f of x equals 1 over 5 e to the negative x over 5, where x is greater than 0. We are asked to find the probability of x being greater than 8. So at this point, we'll plug in by starting to integrate from 8 to infinity of 1/5 e to the negative x over 5 dx. Now, this point will integrate, so we have 1 over 5 multiplied by negative 5 e to the negative x over 5. And we'll take this from 8 to infinity. So this will become the limit as x approaches infinity of negative e to the negative x over 5 minus negative e to the negative 8 over 5. If we take the limit, that's going to be equivalent to 0 plus e to the negative 8 over 5. And this will equal 0.20. So to answer the question, what is the probability a given component is still functioning after 8 years? The answer is 20% or 0.20. Very good. Now at this point, let's talk about the gamma distribution. Now the gamma distribution does have a relationship to the exponential and the Poisson distribution. We'll examine that closely. So for the exponential distribution, it described the time between the time until a Poisson event occurred or the time between Poisson events. The gamma distribution describes the time until a specific number of Poisson events occurs. Now, in order to understand the gamma distribution, we first must look at the gamma function. So gamma of alpha equals the integral from 0 to infinity of x to the alpha minus 1 e to the negative x dx for alpha greater than 0. In the gamma distribution, it is dependent on the parameters alpha and beta. Alpha is an essential part of the gamma function. Some properties of our gamma function is that gamma of alpha is equal to the quantity of alpha minus 1 multiplied by gamma of alpha minus 1. Gamma of n, where n is a positive integer, is equivalent to the quantity of n minus 1 factorial. And our gamma of 1 is equal to 1, and gamma of 1/2 is equal to the square root of pi. These properties might be convenient for you to write down or even memorize. So now that we have a concept of our gamma function, we can now examine our gamma distribution. So let x be a continuous random variable with probability density function f of x equal 1 over beta alpha multiplied by gamma alpha, which is multiplied by x to the alpha minus 1 multiplied by e to the negative x over beta, where x is greater than 0, and we'll let it be 0 otherwise. Notice x has a gamma distribution with parameters alpha and beta. Alpha corresponds to the specific number of Poisson events of interest. The gamma distribution with alpha equals 1 is the exponential distribution. I do want to take a second to note about the PDF for our gamma distribution. If you happen to look up online, you may see a slight variation of this. That's okay, they're equivalent functions, but I know in my graduate work, depending on which textbook I used, the gamma function PDF would be slightly different. They are technically all equivalent. For this course, we're going to focus on this PDF. So as we talked about with the exponential function, we do want to talk about the mean and the variance formulas. So for the gamma distribution, our expected value of x is alpha multiplied by beta, and our variance of x is alpha multiplied by beta squared. If you remember when we were talking about the exponential equation, it was almost identical to the mean and variance for the gamma distribution, only there is no alpha parameter. So at this point, let's go ahead and look at another example. So let us suppose that phone calls arriving at a particular switchboard follow a Poisson process with an average of 5 calls coming per minute. what is the probability that up to a minute will elapse by the time 2 calls have come in? We let x equal the time in minutes until 2 calls come in. X will follow the gamma distribution with beta equal to 1/5 and alpha equal to 2. So by plugging in, we can find that f of x, first off, if we call f of x equals 1 over beta to the alpha multiplied by gamma of alpha, which is multiplied by x to the alpha minus 1 multiplied by e to the negative x over beta. Now by plugging in the information from our problem, this would become 1 all over 1/5 squared multiplied by alpha over 2. This fraction would be multiplied by x squared, well, not x squared, sorry, x to the 2 minus 1 multiplied by e to the negative x over 1/5. If we simplify, this would become 25x e to the negative 5x for x greater than 0. This point then, now that we have simplified our PDF, we can now find the probability that x is less than or equal to 1. So in order to do that, I'm going to go ahead and pull that 25 out, actually just so I don't have to flip back and forth. I'm going to just write f of x equals 25x e to the negative 5x, and we know this is for x greater than 0. So as I said, I'm going to go ahead and pull that 25 out. We are going to be integrating from 0 to 1, x e to the negative 5x dx. Now at this point, I'm going to use the u substitution. So I'm going to let u equal x and du equal dx. And I'm going to let dv equal e to the negative 5x dx and v equal negative e to the negative 5x over 5, which, if we recall, if you integrate u dv, this is going to be equivalent to uv minus the integral of v du. So I'm just going to put that in a box to help us out. So now at this point, we will integrate. So this will equal 25 multiplied by the quantity of negative x e to the negative 5x over 5, which we will integrate from 0 to 1, or plug in from 0 to 1, minus the integral from 0 to 1 of negative e to the negative 5x over 5 dx. Let's go ahead and simplify and integrate. So this will become 25 multiplied negative e to the negative 5 over 5 minus e to the negative 5x over 25, which we'll take from 0 to 1. Simplifying again, this will become negative 5 e to the negative fifth minus e to the negative 5th plus 1. And if we type that into our calculators, we will get 0.96, thereabouts. All right, very good. So the answer to the question, what is the probability that up to a minute will elapse by the time 2 calls have come in? The answer, 96%. Whew, very good. Okay, so this leads us to talking about the chi-square distribution. Now, we're going to talk about this very, very briefly, as in we're going to only spend one slide on talking about the chi-square distribution today. But I do want to tell you the chi-square distribution will come up later in the in the course, but it's not our main focus of this particular lecture. So the chi-square distribution is actually a special case of our gamma distribution where alpha equals v over 2 and beta equals 2 for some positive integer v. Our parameter v is called the degrees of freedom of our chi-square distribution. For the mean and the variance of the chi-square distribution, it is going to be that our mean is equivalent to V and our variance is equivalent to 2V. And as I already said before, this is all I'm going to spend, the time I'm going to spend on the chi-square distribution for this lecture, but it will pop up later in the course and we'll explore the chi-square distribution more then. So now let's take a look at the beta distribution. So for the beta distribution, we're going to let x be a continuous random variable with probability density function f of x equals gamma of alpha plus beta over gamma of alpha multiplied by gamma of beta. And this is going to be multiplied by x to the alpha minus 1 multiplied by 1 minus x and quantity to the beta minus 1, where x is on the bounds from 0 to 1, and we let it be 0 otherwise. With our PDF, this means that x has a beta distribution with parameters alpha and beta both being greater than 0. For the beta distribution, our mean is going to be alpha over alpha plus beta, and the variance will be alpha multiplied by beta all over the quantity of alpha plus beta squared and quantity, or excuse me, the quantity of alpha plus beta, that quantity squared, multiplied by alpha plus beta plus 1 and quantity. And for us, we want something to be of note. The beta distribution with alpha equals 1 and beta equals 1 is actually the uniform distribution on the bounds from 0 to 1. And just like our chi-square distribution, I am not going to talk more about the beta distribution. You know the PDF, you know how to find the means and variance, and for this course, that's pretty sufficient for right now. We may explore that distribution later if we have the time. So what we're going to do now, and for the remainder of this lecture, which isn't very much, we're going to talk about the log normal distribution, which, as you can imagine, has a relationship to the normal distribution. So if we let z have a standard normal distribution, then x equals e to the quantity u plus sigma z has a log normal distribution with parameters mu and sigma, and y equals to the natural log of x has a normal distribution with mean, mu, and standard deviation sigma. This means our probability density function for x is f of x equals 1 over the square root of 2 pi multiplied by sigma times x, which is multiplied by e to the negative 1 over 2 sigma squared, which is multiplied by the natural log of x minus mu quantity squared, where x is greater than 0, and we let it be 0 otherwise. For our log normal variable, it is dependent on the parameters mu and sigma, just as it was in the normal distribution. For the log normal distribution, our mean is equivalent to e raised to the mu plus variance divided by 2. And the variance of x is actually equal to e to the 2u plus sigma squared multiplied by e to the sigma squared minus 1 and quantity. And we like to use, when taking the natural log of random variable results, to a random variable with a normal distribution. Let me rephrase that because I feel like that came out a little funky. We're going to use this when taking the natural log of a random variable results in a random variable with a normal distribution. So that's why you see the double variances. So suppose x follows a log normal distribution with mu equal to 3.2 and sigma equal to 1, and we are asked to find the probability of x less than or equal to 8. So in this case, we would have the natural log of x follow approximately the normal distribution with 3.2 as our mean and 1 as our standard deviation. So if we want to find the probability of x less than or equal to 8, that will equal the probability of the natural log of x less than or equal to the natural log of 8. At this point, we can say that the probability of z less than or equal to the natural log of 8 minus 3.2, all divided by 1, which is equal to the probability of z less than negative 1.12. Using our z-table, we can calculate our probability to be 0.1314. Not bad, right? Okay, so this brings us to the end of this lecture. Let's just take a quick summary of all that we covered. So first, we talked about the exponential distribution, which describes the time between a Poisson event occurs or the time between Poisson events. Then we talked about the gamma distribution, which describes the time until a specific number of Poisson events occurs. Then we briefly talked about the chi-square distribution as a preview to what we'll talk about when we cover chapter 10. Afterwards, we talked about a special case of the uniform distribution, which is called the beta distribution. And then we quickly learned how to find probabilities for a log normal random variable using the normal distribution. Okay, that's it. And as always, if you have questions, please send me an email. Have a good night.